Okay, we are going to do our last lesson of this chapter today. And so the first thing that we're going to talk about is an electric field. And this should be somewhat familiar because we've talked about a gravitational field. And you could say that electric field is similar to it. Um, you know, um, things don't have to be touching the earth to feel the effects of gravity, right? And so we say that something might be interacting with Earth's gravitational field, right? The moon, for example, is interacting with Earth's gravitational field. And similarly, if we have a positive charge here in the middle, we could have a negative out here, and even though these aren't necessarily touching, right? This negative electron might be orbiting the positive proton, and we would say that the negative electron is in the electric field of that proton. So they're not touching, but they are still interacting with that field. Okay, and this is very similar to the gravitational field. We would draw the electric field lines the same, but the one main difference between an electric field and a gravitational field, remember, a gravitational field you cannot shield, right? You can't put something in between you and the earth and go, oh, now gravity of the earth is not affecting me anymore. No, but you can do that with an electric field for example, air itself, right? An electric field is going to be much stronger in a vacuum, whereas in the air, there's some things in the way, right? There's some obstacles, and so the electric field may not be as strong. Obviously, you could even put other things in the way, such as metal. Metal is a great shielder of electric field. It's a good conductor when there's actual contact or if it's close enough, but you can get things in the way of the electric field. Okay. Um, let's talk a little bit about the strength of electric field. Okay, there's a little formula that we're going to use. We're going to say that the electric field strength, capital E, is equal to the electric force divided by the amount of charge in the item that we're talking about. Okay, all right, so we're talking about the charge is like the electron in this case. The proton is at the center, and the electron, we would say that it's in the electric field based on the charge of that electron. Okay. Now we're going to say that if we have a negative charge somewhere, that a positive charge that enters the electric field, right? We can talk about field lines, kind of like we did with gravitational lines, right? We're going to have these electric field lines, but this time direction matters, right? Because if we're talking about a positive somewhere out here, then it's going to be going in this direction, right? But if we're talking about some negative out here, well, now the field lines go in the opposite direction because we're talking about a repulsive force. Okay, so gravitational field lines, electric field lines look the same, but you just got to make sure you pay attention to the direction based on what is outside or interacting with that electric field. Okay. Now, sometimes, if this is when we have, how do I want to say it? These are electric force lines emanating from one body, right? But we could have the situation where we have a positive and a negative charge that are emanating from two opposite charges, and so we would say this is kind of important as far as the direction, right? The force lines would go in this direction. Now remember, these things are emanating, right, from all parts of that positive, and so we might draw lines like we did, like this kind of looks a little bit like a magnet, right? Now we can't really see that, but right? So our force lines might look something like that. Now there's other force lines coming in, right? We're just not going to draw all those, okay? But when we have two objects that are emanating force fields, then we might have electric field lines that look like that, okay? So just keep in mind that when we draw field lines, we're going from positive to negative if there's opposite charges, all right? So that's about it for electric force lines, electric field lines, excuse me. Okay, and also keep in mind, and I don't draw them, I don't know how you can draw them, that really the electric field that's emanating from a single charge is 360 degrees, right? It's actually spherical. Now we draw it as kind of circular, but really it's spherical. It's going up and it's going down from that charge. So keep that in mind. All right. Okay, so the last thing that I want to say, well, there's actually two things I want to say about electric fields, is that there's a lot of energy in the electric field. And it's actually the electric field that we use to draw our electrical energy from, right? So we can accelerate an object through that electric field, or we can move that electric field through a conductor in order to get energy from one place to another, okay? So the electric field does have a lot of energy. Now, the electric field we may not see the direct evidence of, but yet we have to know it's there. And this is actually the how the microwave became invented. A guy by the name of Percy Spencer, he was working in the early mid 1940s. He was experimenting with electrical oscillators, right, in a vacuum tube. They were trying to do some particle accelerating, and so he was working with electric fields basically. They called them electrical oscillations. And he had a candy bar in his pocket. And he went to go eat the candy bar after a while, and it was completely melted. So he kind of thought, there's something that is heating that thing up. And it wasn't too long after that that the first microwave was actually invented, because the electrical field, right, was creating heat because it was colliding with different other things in the air and creating enough heat to melt the chocolate in his pocket. And that's kind of the way microwaves work, is they cause things to collide with other things, specifically water molecules, to collide with the other nonpolar molecules in your food. And just those collisions, those rapid, obviously very, very fast with high energy collisions happen, and that's what heats up your food. So just a little side note there. Okay. One other thing I should have mentioned when I was talking about shielding, not only is metal a good shield, but oil actually is a good shield. Oil shields 100 times better than air. So just another little piece of trivia there for you. Okay, now this is the cool thing about electric shielding. Let's say that we have a sphere, okay, and that sphere has a negative charge. What happens to all the electrons in that sphere? Well, first of all, we need to have a better sphere. So let me see if I can actually use one of these. Whoa, look at that. Oh, nice. Okay, so there's a nice sphere. What happens is all of the charge, they're all negative, right? And so they're going to repel. And what happens is all the charge gets spaced equally on the outside of the sphere. It all gets pushed to the outside of the sphere. And what happens is on the inside of the sphere, there's no charge. Kind of cool, right? Because all of the negatives, this is a negatively charged sphere, of course, so all the electrons are pushed to the outside. So everywhere on the inside, there's no charge. Now, you might think, well, that can't really work all the time, right? For that's only in the middle, because all the charges are equal distance. Well, let me draw that sphere again. Okay, I gotta get good at this. I'm gonna draw this a little bit bigger, maybe. How can I draw it bigger? There we go. let's say that we are talking about, again, we're a negatively charged sphere and all the negatives on the outside. Let's say we're going to talk about a point right here. And you might say, well, because it's closer to the right side, right, this distance right here is closer to the right side, then it should have a stronger attraction to that right side because it's closer, right? Well, what happens if we, because remember that electrical force is not just based on distance, it's based on distance and charge. Okay, so you have all these charges again on the perimeter, so keep that in mind. So this distance, let's say that this distance is double, right, which would make the electrical force 4 times as big over here. Okay, so keep that in mind. I'm going to come back to that, but for right now, let me erase this just for drawing purposes. Now, if we also have to consider the charge, right? Well, let's look at the distance from the charge to this particle or this point in the middle, okay? Remember, we're talking about a three-dimensional object here. So we want to imagine there's a cone. If we're considering this the edge right here, right? And then we take that same angle, oops, and we get this cone over here. Now remember, this radius was half of this, okay? And so what that means is that this distance over here, let me give you a different color so you can see that. This distance over here is twice that, okay? And so what you get, the surface area on this cone is 4 times, this surface area is 4 times as big as this surface area over here, okay? And so we're talking about the charge. Remember, all the charge is on the outside, so there's 4 times as much charge in this cone as there is over on this cone, or on that surface. I shouldn't say the cone, but in that circle, right? There's 4 times. Well, the distance is going to be 4 times stronger over here, and so they end up canceling out, right? Because this is a shorter distance than this. So no matter where you are, you could draw these cones no matter where you are, and if it's a third of the distance, it's going to be 3 times as strong, but the cone on the other side is going to have 3 times the area. And so those end up canceling out, which is kind of a cool thing. And what that does is that shows us that that there is no charge on the inside because everything is balanced, right? All that charge has been pushed to the outside and everything on the inside is balanced, okay? And that's kind of important. So what's kind of cool about that, let me erase this, is no matter what the shape is, all the charge gets pushed to the outside, right? Let's say that we have a cube, but I'm just going to draw a 2-dimensional cube. All of the charge is going to end up on the outside, but there's going to be more charge in the corners, right, because of how a cube is. And similar to a lightning rod, charge is going to line up more at points than it will anywhere else. But the other thing I think is that in the middle here, no charge. Okay, but on the outside, all the charge is there, not necessarily equal distance. There's going to be more on the corners. If you had a figure that was kind of egg-shaped, right, but still had a point there, I'm not doing well here. All the charge would be equal out here, all right, but then it would start to kind of build up on that point there. Okay, so you'd have more charge on that point. All right, now why is that kind of important for us? Let's see. If there were an electric field inside of a conductor, then free electrons inside the conductor will be set in motion, right? So let's say that let's say, let me get rid of this. Let's say we were looking at a wire, right? If we then apply a charge through that wire, right? We charge that thing up. All the electrons are going to start moving around, but because they're all electrons, again, they're going to repulse and they're eventually going to move to the outside. Okay, and what we have is no charge in the middle. Now, why is that important? Here's why it's important. If you ever are in a vehicle that a power line falls on or it gets hit by lightning, you stay in the vehicle because all the charge will go immediately to the outside of the car. Okay, so you're safe as long as you're inside the car. Okay, if you get out of the car, right, if you open the door and you step on the ground, you have now entered that electric field. And not only that, but you've given the electricity somewhere to go because you put your foot on the ground and the electricity is going to go through you. Okay, and so the recommendation is you open the door and you jump from the car. And not only that, you want to, well, we'll talk about this other part later, but just jump from the car and then roll away and get away because all the charge on the outside of the car. All right. I think that's about all I'm going to say about electric fields. Okay. All right. Let's talk a little bit about electric potential. This is kind of about how much energy something could have, right? We talk about potential energy, right? We talked about that. That's how much energy something could have. And remember, it was based on a couple of things. Potential energy was based on either how high we lifted something or how much we compressed a spring or something like that, right? Or how fast or how slow something was moving. That would determine its potential energy. Well, electric potential energy is very similar. Electric potential energy has to do with how much work is required to push or pull a charged particle against an electric field of something else. So let's say that we have a sphere and I have a little electric charge over here, and we will call both of those sorry, I shouldn't do that. There's positive all throughout this sphere. Okay, so this little guy over here obviously is being repulsed, right? Because they're all the same charges. But if I was to push that charge, let's say that far, there would be a certain amount of work required, but I could push that little charge against the electric field, right? That's pushing against that thing, okay? And so there's a certain amount of work. Now, if I was then, once it got to this point, right here, if I was then to let it go, well, where would that little tiny electric charge go? Well, it'd go flying back that way, right? And the amount of energy that it has would be equal to the amount of work it took for me to move it in the first place. And this is kind of what electric potential energy is. This is how much energy a particle possesses, right? Based on its location to another charged object. Okay. Let's do the drawing where we talk about, we talked about a pulley and a string, a rope that is carrying or holding up a box, right? And that as we lift that box up, right, its potential energy increases until I cut that rope, and then that thing goes crashing down, and now it has kinetic energy, right? This is a pile driver example. Well, it's very similar for electric charge, right? Let's say that I have a negative down here and this is a positive. These things want to attract. So if I pull that positive up this way, I mean, the farther I pull it, the more I'm increasing the potential energy, right? Until I let it go and it slams into the negative charge here at the bottom. Now that potential energy has just become kinetic energy, right? So keep in mind that a particle that has twice as much charge, right, will have twice as much potential energy, right? And if it has 3 times as much charge, it'll have 3 times as much energy. And obviously, if I double the distance, I double the potential energy. If I triple the distance, I triple the potential energy, okay? Now, we want to talk about electric potential energy per unit of charge, right? So we're talking about the Coulomb, and so when we talk about electric potential energy, all right, electric potential energy, we're talking about how much energy something has per Coulomb. Okay. Now, what does energy come in units of? You can pause it now and think about it, but the answer is joules. Okay. So if I have something, well, let's see. Let me back up a little bit and say, so if something has 10 joules of energy per 10 coulombs of charge, that'd be the same as something having 1 joule of energy per 1 coulomb of charge. So it's not just the charge that matters, but also the energy within that. And the energy comes from the work done to move something in place into or out of an electric field. Okay. Okay, so now this is where things get a little confusing. So if you need to pause and rewind, that's okay. All right. There's another term that we're going to use here that sounds a lot like electric potential energy, but it's just called electric potential. Okay. Electric potential is equal to electric potential energy over charge. Okay, now electric potential energy is energy, right? And as we just said, the units of energy is joules, and the units of charge are coulombs. So electric potential is joules over coulombs, okay? Now, we have a name for electric potential. You've heard this name. We don't ever call it electric potential, right? We call it volts. So electric potential is a volt. So 1 volt is equal to 1 joule per coulomb, okay? So we've heard of a 12-volt battery, right? So what does that mean? It means that it gives 12 joules of energy to every 1 coulomb of charge that passes through the battery, right? Your little AA batteries, those are 1.5 volts. So those give 1.5 joules of energy for every 1 coulomb of charge. Okay. Now, I don't know if that sounds like a lot or not, but remember that a coulomb itself is a pretty large amount of charge. Okay. And so we're kind of dealing with different things here. So think of voltage, and this is the best way that I have to think of it, but voltage is like pressure. It's how hard, electric potential is how hard electricity is pushed. Okay, so like, let me give you this example. Let's see if I can draw this. I didn't like that. Let me just clear this whole thing. Okay. Okay. So let's say if I have this situation, this is a higher pressure than this. And so if I apply higher pressure here, what's it going to do? Well, it's going to want to make those even, right? It's going to take this down and it's going to take that up. And that's what pressure does to liquids. Well, it's very similar to that with electricity. When you have voltage, it means that there's a high pressure area and then there's a low pressure end. And it always wants to go from the high pressure towards the low pressure. Okay, so if you rub a balloon on your hair, for example, the balloon becomes negatively charged, all right? And you might be surprised to hear this, but a balloon could have about 5,000 volts when you rub it against your hair, and that sounds like a lot, right? That's 5,000 joules per 1 coulomb of energy, right? Now that would be a lot if there was enough charge, okay? But the amount of charge in a balloon is, oh gosh, didn't do that very well. the amount of charge in a balloon is about a millionth of a coulomb. Why is this not writing? There it is. 1/millionth of a coulomb, right? So there's a lot of potential, but not something that's going to necessarily hurt you. Okay, so a high voltage means there's a lot of energy only if there is a lot of charge involved also. Okay, so there's an important difference between electric potential energy and electric potential. All right, you can have something that has a very high electric potential. Has a lot of electric potential energy, but maybe not a lot of electric potential. Okay. And we'll get to this more in the next chapter, and it will help clear it up as we talk about volts and amps and all that kind of stuff, all right? Okay, now what's kind of cool about this is that you can actually create a battery based on electric potential. And what we're really going to call it is a capacitor. So a capacitor is something that can store energy, okay? And the way that we can make a capacitor, just a simple way, is let's say you have a battery, right? This is the positive end, this is the negative end, and this end is going to be tied to a plate, okay? And this side is going to be tied to another plate, and we're going to have some positive charges are going to go over here. So the way a battery actually works is it's going to allow negatives. Hold on. It's going to allow negatives to flow. Okay, get the right colors. Out of this capacitor has both positive and negatives to start. This plate, I'm sorry. Okay, these are like metal plates. So it has both positive and negatives. But when you hook it to a battery, what it does, it allows the electrons to flow out and through the battery and this side, and it's going to end up coming onto this plate, so that this plate becomes negatively charged because it gains a bunch of electrons, and this plate is going to become positively charged because it loses a lot of electrons. Okay, all right, so the capacitor then has equal but opposite charges, right? We have the positive connected to the positive battery terminal and the negative connected to the negative battery terminal, right? So the charging process is finished, right? We're charging these plates. It's finished when the potential difference between the plates equals the potential difference between the battery terminals, right? Or the voltage, right? So the larger the voltage of this battery, the larger, let's see, how do I want to say it? The greater the charge that can be stored, right? So now you have a lot of charge on here. It's all negative charge, and you have a lot of positive charge over here, right? But the bigger this battery, more flow can go through here, and we get even greater charge. Now, the closeness of those plates will also affect how much charge can be held, right? So in reality, the plates might be really thin foils separated by a thin sheet of paper, right? And then they might roll it up and they might make a capacitor. You've probably seen capacitors. I'm going to show you some tomorrow because I'm going to get some from my father-in-law, but it might look like a thin wafer with two little wires coming out of it, something like that. Or it might be like a little cylinder with a couple wires coming out of it. But all that is these thin plates, and then when you hook these terminals up, right, to a battery of some kind or a power source, then it can store electric charge, right? Negative on one side, positive on the other. Which is actually why, let me back up. This is actually the technology that's used in flashes, in defibrillators, right? This is a way that we can store energy, and obviously in electrical circuits, this happens as well. You know, sometimes we power down our computer, right? Or we might even unplug it. Well, there's still electricity going on because there's power that's been stored in these capacitors, and it is slowly letting that power back out to keep things kind of running, like the time or the date or whatever it needs to run. Okay, so remember that the net charge here of this capacitor is 0, right? Because it's got an equal amount of positive and negative on each plate, right? So the net charge of the whole system is negative, okay? This is one other reason why you might see warning labels on things like don't work on this unless you unplug it. Even though a TV might be off, you could be working on its components and there's some stored energy in the capacitors, and if you connect them, or if you make them touch somehow, if you put a screwdriver that crosses both terminals, there's going to be an opportunity for that charge to leave the capacitor and through your screwdriver, and you're going to send a shock and spark and all kinds of problems, okay? So capacitors are very important, but they can also cause some problems if you don't know what you're doing. All right, which leads us to this little apparatus that I know you've seen before because everybody has done this, but you've seen the globes that have lightning sparks coming off of it, right? This is called a Van de Graaff generator, named after Robert Van de Graaff, right? In 1931, he came up with that. They were trying to smash atoms by, again, using particle accelerators. And they were sending these particles at very high speeds and then smashing them into target atoms and trying to remove a proton or a neutron from the nucleus of an atom, and they actually were successful at this. And so what it did, though, is because there was such energy, so like if you have a atom, right, and you got some protons and neutrons in here, if you remember I talked about the nuclear force, right? You got a couple of protons in here and you can knock one out. The amount of energy that's holding these together that now gets broken, it gets released, and you get a lot of energy. This energy comes out in the form of X-rays or gamma rays, right? Hence the comic books came out of this era as they started to do this. And so we need this energy, right? This is the energy that led to nuclear energy, and obviously we use X-rays and stuff like that, okay? But he also made a lightning machine, right? So the lightning machine that you see in the movies, or the ones where you put your hand on it and it goes to the lightning bolts go to your hand, all it is what's called a Van de Graaff generator, okay? And so what I want to encourage you to do is go onto YouTube, look up this Van de Graaff generator, and just kind of see. You can kind of see one in action if you have not. But basically what it does is let's see, the Van de Graaff generator is kind of up here like this, and it's got this motor down here at the bottom, okay, and there's a belt that runs up and back down, okay, and so the motor turns this pulley right here, okay, and the belt goes back and forth, and it actually creates some friction on the belt, and that there's little wire metal pickups right here. And so what happens is through the conduction, negative charges go up into that little metal thing, and we get little negative electrons get pushed to the outside of that thing, okay? And so obviously when you touch it, right, it gives you, now you've given a place for those electrons to go. They tend to go up in your hair, which is why you'll see people's hair stand up on end, okay? But remember that the net charge on the inside of that metal sphere is 0, okay? So not a real exciting thing, but it's kind of cool to know that, it's not enough voltage necessarily to hurt you, but it's kind of a fun science experiment. So take a look at that when you have a chance. All right, that is it for this lesson on electric fields and electric potential. Rewind it and look at it as many times as you need when you go to answer your questions, and we'll talk to you later.